Trouble with Zoom, and yeah, thanks for waiting. So maybe we should get started right away. So this is the last colloquium for this year, and we are ending on a high note with a terrific colloquium and a great panel. So I'm really pleased to introduce Robert Huang from Caltech. He's jointly advised by John Preskill and Thomas Vidic, and he's done really foundational work on classical shadows and on how to use these in learning algorithms and to get around this data bottleneck. So really looking forward to your talk, Robert. Would you be able to share your screen?
Yep. Okay, then should I just start? Yeah, my name is Robert, and for today's quantum colloquium, I'll be talking about making predictions in the quantum world. I will cover a series of work in collaborations with Richard Kueng, John Preskill, Steve Flammia, Jarrod Cotler, Sitan Chen, Jerry Lee, Michael Broughton, and Jarrod McClean. So one of the central goals in many scientific disciplines is to learn how the physical world operates. Here we consider learning as the combination of receiving, processing, storing information, such that subsequently you can use the stored information to make prediction about the future of the physical world and how one should engineer it to provide certain benefits. So previously, classical learning theory have provided a lot of the foundations for understanding how an agent could learn about classical functions, classical distribution, etc. However, the physical world that we live in is intrinsically quantum, so it's very important to understand the generalization of classical learning theory to learning about quantum states, quantum processes, and so on. So here in this talk, I would cover some of the recent progress in developing a theory for learning about a quantum mechanical world. The outline for today's talk is as follows. I will separate the talk into 3 parts. The first part would talk about learning with a classical agent, on understanding what's the power of classical agent, what can it learn, what can it not learn, and so on. And in the second part of the talk, I will dive into talking about learning with a quantum agent and discuss what kind of quantum advantage could we obtain over classical agent. Finally, I will present experimental demonstration of the quantum advantage achieved by quantum agents on the Sycamore processor. So let's begin with the first part of the talk. So here we will consider a classical agent, which is an abstract model for a scientist, an experimentalist, or even classical machine learning algorithm, etc., where this classical agent can interact with a physical world that's operating quantum mechanically. The classical agent could conduct experiments by providing some instruction for how one experiment should perform and obtain experimental outcome from the physical system in order to learn about the physical system. So let's begin by defining what one experiment is. So this is just a formal definition. One could tweak around with the definition, but here's one general form of definition that one could use. So here we would consider classical agent to specify some action. So these are parameters that control the physical system by the classical agent. More generally, we consider this form of having first perform X, followed by Y1 to YL, and finish with Z. So what this XYZ meant will become clear very soon. So the instruction would be provided to the physical system to conduct one such experiment. And what the physical system would do is, depending on what this X is, the physical system will prepare a quantum state rho X, which represents a quantum many-body system. This quantum system could be very, very complicated. For example, one could consider this input X to represent some Hamiltonian of a many-body system, and this rho X corresponds to the ground state of such a Hamiltonian, let's say H of X. So, but it could be also a very simple form. Like for example, the X just corresponds to, rho X just corresponds to preparing the all zero state. So this is just a general framework for for preparing the state, which is parameterized by this input x. And then in the next step, the physical system will evolve the system, will evolve the state with rho x under some quantum many-body dynamics, which is represented by a CPTP map EY1, which is a general representation for all possible quantum dynamics, not just unitary dynamics, but also some stochastic dynamics and so on. So this evolution will be specified by the second action of the classical agent. So Y1 corresponds to the evolution that we perform. And follow up on that, depending on what Y2 is, the physical system will then evolve the state under a second evolution, EY2, and the physical system would just go do the evolution up until E of YL. And now the state prepared in the physical system is shown above. And at the end, what we would do is we would perform, what the classical agent would do is it will perform a measurement on the physical system represented by a POVM MZ, which collapses the state and produces a measurement outcome for the classical agent. The classical agent could conduct multiple experiments. For example, he could start with some instruction for one such experiment, obtain the measurement outcome. Depending on the measurement outcome, design a second set of experiments, obtain it again, and do that and repeat this process for multiple rounds. So this is a very general, this is a very abstract model for essentially all possible kinds of experiments one could perform in physical sciences, such as in quantum experiments, or even in chemical experiments, or in other kind of experiments. And depending on the situation, changing some of the parameter might be easy or hard. Like for example, maybe changing X is pretty difficult, but changing Z, like what is the basis that one measures, is much more easier. However, we're just going to throw away all of that detail and just focus on this abstract form to discuss what kind of classical agent learn about the physical system. So one of the key questions that we would like to understand is, through this interaction with the physical system, what can the classical agent learn? Can it learn what's the state being prepared? Can it learn what's rho x? Can it learn what's EY, or can it learn what's MZ? Or can it learn to predict properties about the state being prepared, and so on? So before diving into some of the content, I would like to review some of the results discussed in John Preskill's talk at a previous quantum colloquium held at April 27th, which illustrates some of the predictive power of a classical agent. So in John's talk, he had presented this classical shadow formalism, which is a procedure that we proposed last year. In this classical shadow formalism, we assume that some of the evolutions are known and one of the measurements is known. So basically, when the classical agents specify an action Y that's in the Clifford group, the associated evolution EY, shown here, is, we assume that it's the ideal Clifford unitary. On the other hand, if the classical agent said perform Z equal to 0, then the measurement M0 corresponds to the ideal computational basis measure. So that's a key assumption used in classical shadow formalism when one treats in this more general framework. Basically, what classical shadow formalism tells us is that given any x that's such that this rho of x is unknown, the classical agent can perform very few amount of experiments to predict many properties of this unknown quantum state rho x using this proposed classical shadow formalism. Building on classical shadow formalism, one can perform a great variety of different quantum many-body problems. For example, one could consider using classical ML combined with classical shadow formalism to classify various quantum phases of matter, including SPT phase, topologically ordered phase, and so on. Basically, in this recent work published around half a year ago, we showed that one could train the classical agent such that given a new x corresponding to some unknown rho x, the classical agent can perform a polynomial number of experiments, here polynomial in the system size, to accurately predict the quantum phase of rho x. So here, we're utilizing the same assumption as classical shadow formalism. We're assuming that some of the evolutions are known and one of the measurements correspond to M0 is known and it's the ideal computational basis measurement. Another application of classical shadow formalism that illustrates the power of classical agent is for predicting ground states. Here, we go back to one of the examples that I mentioned. We consider rho x to be the ground state of some gapped Hamiltonian h of x living in some finite spatial dimension that's parameterized by this m-dimensional vector x living in some hypercube. In this paper, we proved that after performing a polynomial number of experiments, polynomial in this M and independent of system size, the classical agent can efficiently learn to predict the ground state properties of this Hamiltonian h of x for any x in this hypercube, in this m-dimensional hypercube, to a constant average error. Again, here we're utilizing the same assumption as classical shadow formalism. So as you can see, some of these applications, classifying quantum phases, predicting ground states, are often being said as the application of quantum machine learning algorithm. But here you can see that using a classical agent interacting with the physical system plus a classical machine learning model, one could achieve these tasks to some degree. So like, for example, it's constant average error, and there are some restriction on what kind of quantum phases of matter one could predict. However, the key take-home message from John's talk or from these previous results is that classical agents are really quite powerful at learning about quantum systems and solving quantum many-body problems, especially when some of the evolutions and measurements are perfectly known. Like in the assumption of classical shadow, we assume that this Clifford group is known, a Clifford unitary is known, and the computational basis measurement is also perfectly known. However, it raises the following very natural question. What if none of the states, none of the evolution, and none of the measurements in the physical system are perfectly known? Can the classical agent still achieve its original power, or can it still learn certain things that are useful, or things just breaks down? So this is a pretty tricky question and kind of hard. So in order to better understand what the classical agent can learn under this more general situation where nothing is known, we have to first provide some formal definition. So the first definition that I would consider is called world model. So the world model basically just specifies the physical description of each action. For example, when the classical agent said do X, what is the actual quantum state rho X that's being prepared? When it say do Y, what is the actual evolution EY, and so on. So formally, a world model is just a collection of this mapping from the action XYZ to the corresponding physical operation rho X, EY, and MZ. So in physical reality, the classical agent will live in some world model, which we call the true world model. However, the classical agent doesn't know what this true world model is, but he or she has a set of candidate world models, which is denoted as a model class Q, which is just a set of all possible candidate world models, including the true world model. And what the classical agent tries to do is he would try to learn what this true world model is among the candidates in this model class Q. And we say this model class, which is just a set of all candidate world models, is learnable if whenever the true world model lives in if it's inside this Q, the classical agent can learn all the physical operation in the true world model. So here we do note that it's up to a global unitary or anti-unitary transformation, which is intrinsic in quantum mechanics. It's also discussed in this theorem known as the Wigner theorem. There's this degree of freedom in quantum mechanics that one could choose freely. So again, here we're going to consider classical agent learning the physical operations up to this global unitary or anti-unitary transformation. So that's a very quick summary of the definition for this task. And now we could try to understand what is learnable, what kind of situation is learnable for a classical agent, and what are not learnable. So we would begin by providing a sequence of examples demonstrating what are situations that's unlearnable, starting from the simplest one shown here. So here we consider a model class consisting of two world models, candidate world models A and candidate world models B. Essentially, what the classical agent tried to do is to understand if it's living in world model A or world model B. So in this situation, we consider a very simple qubit system with only 4 actions. The first action prepares some state. The other 2 actions in the world model A evolves the state under Hadamard gate and the phase gate. And finally, the last action, which corresponds to a measurement, performs a perfect computational basis measurement. In world model B, however, the 2 evolution actions becomes too noisy, and it's now just producing a completely mixed state, no matter what state you're putting in. So as you can see, the 2 world models are physically, like they describe physically different reality. In particular, for people well-versed in gauge set tomography, these 2 world models are not related by a gauge transformation. However, it's impossible for the classical agent to distinguish between the 2 world models because the states in both cases is a complete mixed state. So no matter what experiment, so we call that one experiment means a sequence of X, Y1, Y2, Y3, finishing with Z. No matter what experiments the classical agent performs, the resulting outcome is going to be a uniform distribution. And that's why the classical agent will not be able to distinguish between the 2 world models. So this is just a very trivial example of a situation that's unlearnable. However, one could consider a less trivial example that's still unlearnable. So in this situation, we consider having, again, 2 world models where they both prepare a perfect zero state, can perform a perfect computational basis measurement, can implement the phase gate perfectly, but for the Hadamard gate, it will be subject to some noise. So for world model A, it's after applying Hadamard gate, there's a small chance, an epsilon probability of having a bit flip error, X error happening on the state. On the other hand, in world model B, there's a small chance of having a phase flip. This is a pretty usual scenario that people often consider. There are some incoherent noise happening in the device, and we just wanted to figure out which is which, whether it's more likely to have bit flip error or phase flip error, so then we can tune our device to better combat these kind of errors. So now, basically, we're going to show is that these 2 world models are, again, indistinguishable. They're unlearnable. It's impossible for the classical agent to figure out if it's in world model A or world model B. To get a better understanding for why that's the case, let's consider a very specific experiment. So let's say we start from X equal to 0. Let's say the classical agent instructs the physical system to perform X equal to 0, which prepares this perfect zero state. And now let's say the classical agent conducts a Hadamard gate after. So in world model A, because bit flip error actually leave plus state unchanged. So after this action, the state in world model A is just plus state. On the other hand, for world model B, it will be a different state because they're different physical reality. However, when the classical agent performs a second Hadamard gate, suddenly the 2 states in the world models become the same. Basically, for world model B, PZ will now act as an identity, but PX would actually change the state to become this mixed state. So since the state in the 2 world models are the same, when we perform a perfect computational basis measurement, we're just going to see the same output distribution, 0 with probability 1 minus epsilon, and 1 with probability epsilon. So as you can see, at least for this experiment, it's impossible for the classical agent to determine if it's in world model A or world model B. However, using some proof technique, one could show that for all possible experiments that the classical agent could do, the output distribution is going to be the same in world model A and B. And that's why the classical agent is never able to learn which physical reality he or she or it is actually in. And the situation is actually even worse. Even if we add in another gate, the T gate, and we assume that it's just a perfect T gate. So now in world model A, one could perform perfect T gate. In both world model, one could perform perfect T gate. Even with this universal gate set, Hadamard, phase gate, and T gate, the classical agent is still unable to learn whether it's in world model A or world model B using a similar proof technique. This could even be further generalized. So the situation is even more challenging in a sense that even if the classical agent can approximately prepare any state, any quantum state, again, apply T-gate perfectly, Hadamard gate perfectly, and apply any Clifford gate up to a Pauli noise. So a Pauli noise is just a probability distribution over having some X error, Y error, or Z error. And again, it can perform computational basis measurement perfectly. So now in this setting, there's an infinite number of actions that the classical agent could perform, but it still cannot decide whether for the Hadamard gate, whether a bit flip error happened or a phase flip error happened. So this result can be condensed into the following theorem, stating that gate-dependent Pauli noise, meaning that the noise for each gate, whether it's, and assuming that it's a Pauli noise, it's unlearnable in physical systems, in quantum systems with noisy Clifford gates and perfect T gates under spam errors. So it's important to note that there have already been a lot of works on like learning quantum processes, learning quantum states. Oftentimes people assume that, let's say, the state preparation and the measurement are perfect and so on. In those kind of settings, people can learn the quantum process using just Clifford gates. However, as one could see, when everything has some noise and everything is unknown, learning becomes very, very challenging. And it's pretty likely that we will encounter these kind of unlearnable situations and so on. So given these results, one would ask, then are there even situations that it's actually learnable? Is it true that actually all situations are unlearnable? Or actually there are some classes of models where we can actually learn things? In order to answer this question, in order to make progress on answering this question, we present the following theorem. We show that given a model class, which is just a set of candidate world models, such that for every candidate world models W, there exists an unknown actions that prepares a pure state. We don't know what the unknown action is. We don't know what the pure state is, but just guarantee that it prepares a pure state. And some unknown actions that form a universal set of unitaries. Again, we don't know what those actions are. And finally, there is an unknown action that performs a POVM with a POVM element not proportional to identity. So the last condition basically just means that the POVM is non-trivial in a sense that when given a POVM such that all the POVM elements are proportional to identity, no matter what state it is, the POVM is just going to produce the same distribution. So it's going to be completely useless. Here, we just need to assume that there's one such POVM such that it's slightly non-trivial. It's not completely trivial. Then we can show that every world model inside this model class, for any world model in this world model class, the classical agent can learn all the physical operation. So basically, at the starting point, the classical agent would just have all these different actions, x1, x2, y1, y2, y3, and so on, that corresponds to all of these different states, evolutions, and measurements that are completely unknown to the classical agent. However, by doing experiments, the classical agent can actually learn all of them. So now, in order to better understand the theorem, let me provide a very brief proof sketch of this theorem. So the first step that the classical agent could do is perform a unitary test. Basically, using the fact that unitary is the only reversible physical process, the classical agent could identify what are the evolutions that are actually unitary dynamics. So let's say the classical agent identified these 3 evolutions as unitary dynamics. Now, what the classical agent could do is he can combine these things randomly, compose them randomly to produce a hard random unitary sampler. So the basic idea here is that a random composition of a universal set of unitaries actually approach to design and even further hard measure. So that's a very important criteria that we're going to utilize. And here's a short animation to just showcase. Basically, the classification can just collect the actions that forms unitary evolution and then just randomly compose them in some way. And then one could prove that by doing random composition, it would actually implement a random unitary sample approximately from the unitary to design. So note that the classical agent still has no knowledge of what's the composed evolution. He doesn't know what's individually what they are. He doesn't know after composition what they are. He just knows that this unknown evolution is guaranteed to be sampled approximately from unitary 2 design. So for those that are not familiar with unitary 2 design, basically it's a definition that considers whether the unitaries are uniformly spread across the space of the special unitary group. So now, by just doing random composition on the unitary evolution, one could generate this tool called the Haar sampler that can generate a random E, that's random evolution E, that corresponds to a random quantum evolution. So now with this Haar sampler, where it would generate some unknown random unitary and some unknown POVM MZ, as long as it's non-trivial, we can actually utilize them to get a state overlap. So we don't know what these Haar random sampling are. We don't know what these guys are. We don't know what rho are. We can still estimate the overlap between rho x2 and rho x3 as follows. So basically what we do is we generate a random evolution from the Haar sampler, apply it onto some state, measure it using some unknown POVM, and then do the same for rho x3 for the other state that we care about, and then follow through this process for different kinds of random evolution that's being generated by this Haar sampler, E1, E2, E3, and so on. Basically, one could utilize Haar integration formula to show that the data collected this way actually enables us to estimate the inner product between any two quantum state. Here is rho x2 and rho x3, without knowing any of the evolution, any of the measurements, and any of the quantum states. So now we have built up this overlap estimator, which can then be used for step 4. So in step 4, what we're going to do is what the classical agent should do is to compose these different states and evolution to form all kinds of states, such that it finds a set of states that satisfy a certain geometry using the overlap estimator. So basically, it's a list of constraints, some rigid constraint that tells us that for the inner product between these two pairs, what should it be, and so on. So it's kind of a long list that's shown on the right-hand side. But using that list of rigid constraint, rigid geometric constraint, one can show that it fixes the state that's being found. Basically, one can prove that using this special geometry, the special set of states that's found must be of this particular form. So some of them are the bases, some of them are superposition of 2 of the bases, and some of them are the superposition of 3 of the bases. These kind of triplet states are actually very important in the proof because the rigid constraint enabled by these triplets allows one to pass information, like pass the relative phase information for a different pair of ij. So that's a pretty important part. So finally, given this special set of states and the overlap estimator that we constructed in step 3, we can actually do quantum state tomography to learn all the states. We can then do quantum process tomography to learn all the processes, and finally do quantum measurement tomography to learn all the quantum measurement. So that's a very short discussion on how one could prove the theorem, which showcase how a classical agent could start from having no knowledge about all the physical operation to having all the knowledge about the physical operation. However, this is only one such sufficient condition where the model, where the classical agent could learn the world model. Understanding when and what kind of model class a classical agent can or cannot learn and how powerful are they under this situation still remain to be a very important open questions. And it would be nice if there are much more results known in this domain. So that concludes my first part of the talk, which discusses some of the power in classical agent and how it could build up knowledge from having nothing, knowing nothing about the physical system. In the second part of the talk, I would dive into talking about learning the world using a quantum agent and discusses what kind of advantage could quantum agent brings and over classical agents. So recall that so far we have been talking about classical agent, which can be thought of as an abstract model representing what scientists currently do in the lab. So scientists could perform physical measurements to receive classical information about the physical system, can process that classical information using classical computer, and storing that classical information in the classical memory. However, as quantum technology advances, one would begin to wonder what a future experiments could be like. So this is also very closely related to one of the previous quantum colloquium by Dorrit Aharonov about quantum algorithmic measurements, which is also providing a framework for understanding what an advantage could quantum technology brings to performing physical experiments. So here, what we consider is a quantum agent that could receive quantum information using quantum sensor, processing that quantum information using quantum computer, and storing the quantum information using quantum memory. A natural question would be, what are the advantages of having a quantum agent that can interact coherently with the system over a classical agent that only interact incoherently, classically, with the classical system? Understanding this question will guide us towards understanding how quantum technology could fundamentally alter our ability to learn about the physical world. So in order to start diving into this question, I would like to simplify the setting a little bit. So previously, I talked about classical agent interacting with these physical systems with unknown states, unknown evolution, unknown measurements, and so on. But here, let's focus on a simplified version where the only unknown in the physical system is some unqubit state rho. So the physical system prepares this quantum state rho where the classical agent can learn about this rho by performing some measurement on each rho for each experiment. On the other hand, the quantum agent can obtain a copy of rho coherently from each experiment. So here's just a visualization for illustrating the setting. The classical agent would have some classical memory, where by performing one measurement on rho, we obtain some classical data that can be stored in classical memory. Another measurement provide a different set of classical bit strings, which can then be used to perform classical post-processing. On the other hand, for quantum agent, what it could do is it could take in rho and store it in its quantum memory, taking another copy of rho, store it in its quantum memory, and then perform an entangled quantum data processing on this collection of quantum data, and then finally implement a measurement to provide some classical prediction. So now, in order to understand what advantage could one have over the other, let's consider the following task. So in this task, we consider the classical and quantum agent so the classical and quantum agent should learn a classical model of this quantum state rho, such that subsequently one can utilize this classical model to predict a large number or just some property of the quantum state rho. So for example, here we focus on the setting where we want to predict the magnitude of the expectation value of some observable P chosen from this set. So such an observable is also known as the unqubit Pauli operator or Pauli observable. And one could prove the following theorem, which is shown in this paper that would come up in 2 days. We can prove that a classical agent actually needs an exponential number of experiments in order to predict just one observable chosen from the set. However, a quantum agent actually only needs a linear number of experiments to predict all the exponentially many observables, all 4 trillion of them. So yeah, so there's this exponential separation between what a classical agent could do and what a quantum agent could do. So in order to better understand the theorem, let me provide also, again, a brief, there's one side note that I want to mention, is that this exponential quantum advantage is present even when the state rho is just a classical distribution over product state. It doesn't need to have any quantum entanglement in this state, in this unknown state rho, in order for this exponential advantage to be present, which is a nice feature and potentially hints at the possibility of using quantum technology in situations that are much more classical than we think. So now let's provide a proof sketch for how one can establish this exponential lower bound for a classical agent. For the upper bound, this linear upper bound on quantum agent, we're essentially using a similar technique that's already been discussed in our previous paper published in January 2021 called Information Theoretic Bounds on Quantum Advantage in Machine Learning. So in order to prove this classical lower bound, we need to understand sort of the dynamics of the classical agent. In particular, let us consider a graphical representation for the memory state of the classical agent. So here, this R corresponds to the root of this tree, which also corresponds to the starting point of the memory state of the classical agent. Every time the classical agent performs one experiment, the memory state would change. Like for example, depending on the outcome, it might change to this point, or this point, and then so on. So in the second experiments, it would change to other points. So note that whenever two memory state would go into the same memory state due to some experimental outcome, it means the information is lost. So it means that the classical agent have forgot something. So in order to consider an optimal classical agent, this should never happen. And when this doesn't happen, one could easily show that the graphical representation of the dynamics of the memory state must be a tree. So essentially, it would start from this root, start branching outward, and after, let's say, T rounds of experiments, this would be a tree of depth T, where there's our leaf nodes at the end, corresponding to the final memory state of the classical agent. In order to understand how well classical agent could learn about the underlying state, we just have to look at this tree representation. So suppose the underlying state is row A, then it would change the sort of the transition probability from one point to another. For example, in row A, it's more likely to go through this transition, but for row B, the three transitions are both equally likely. And basically what one could do is one could just trace over this tree and look at the bottom, the leaf probability distribution. So what is the probability of the final memory state of the classical agent? We need that the probability distribution between the two different underlying states to be sufficiently different in order for the classical agent to be able to distinguish between the two physical reality. So that's a key technique that we are going to use later on. So now in order to prove the lower bound for this prediction task, what we would do is we were going to reduce it to a distinguishing task. More precisely, it's a partially revealed many versus one distinguishing task. So the reason for this partially revealed is that recall that in this task, what we consider is the classical agent will first do the learning. After learning, we will reveal some n-qubit observable P that's revealed. And what the agent has to do is to predict the expectation value of P on this unknown state row. So suppose that the revealed observable is PA. In this case, we can actually set up the problem such that under that condition, the unknown state is going to be one of these three choices, either a complete mixed state or this I plus 0.95 PA or I minus 0.95 PA. So these two states are both just separable states. They're classical probability distribution over product states. So there's no entanglement in any of these three states. And basically, when the classical agent can efficiently predict the expectation value of actually the absolute value of the expectation value that is trace of PA row, then the classical agent could efficiently distinguish between this null hypothesis, because here the expectation value would be 0, while here the absolute value of the expectation will be 0.95. So when the classical agent could perform the prediction test, he would be able to distinguish between the null hypothesis or the alternative hypothesis. On the other hand, if the revealed information, if the revealed observable is PB, we can set it up so that the underlying state is slightly different. And again, if one could achieve the prediction task, he could achieve the distinguishing task. And now, as we discussed before, in order to be able to distinguish between two situations, the leaf probability distribution must be sufficiently different. Meaning that if the classical agent could succeed in the partially revealed many versus one distinguishing task, then it yields a lower bound on the total variation distance in the probability over leaf node. And then what we would do, which is also some of the core technical difficulty, is to upper bound the total variation distance with a function of the number of experiments. So as the number of experiments increases, the total variation distance would also start to increase because they can become more different. However, one could show that the relation between them is very, very mild in the sense that you really need to increase the number of experiments significantly in order to see a substantial difference in the total variation distance. And that's how we establish this exponential lower bound for classical agents. On the other hand, as I said before, the upper bound for quantum agent is already shown in our previous work. So using similar proof technique, one could also establish quantum advantage in a wide variety of tasks. For example, performing quantum PCA. So in this task, the goal of the agent is to learn a fixed property of the principal component, that is the largest eigenvector, called psi, of the unknown state rho. Here we consider the fixed property to be a very simple property, to be the expectation value of the Pauli Z operator on the first cube. Using similar technique, we can prove the following theorem. We can show that a classical agent needs an exponential number of experiments to learn this property about the principal component, but a quantum agent only needs a constant number of experiments to learn this property. So for people that are well-versed in these literature on dequantization, one might be confused and thought, wait, but isn't Ewan-Tan's already shown a polynomial time classical algorithm that could perform quantum PCA? Doesn't this contradict this theorem? So the resolution is the following. So in Ewan-Tan's result, she assumed that there's this oracle, which is called sample and query oracle, SQ oracle or SQ access. And the algorithm must be given that access, given that oracle, in order to achieve this polynomial time computation time. However, one could easily show that constructing SQ oracle from quantum states actually requires an exponential number of experiments, and that's why there's no contradiction happening here. The advantage doesn't only hold for learning physical states, it also holds for learning physical dynamics, where one could consider a similar situation comparing classical agents and quantum agent. In particular, one could show the following. Given a polynomial time physical process E, represented as a CPTV map acting on n qubits, a classical agent requires an exponential number of experiments to learn a model of E that can predict output states accurately on average. However, a quantum agent only needs a polynomial number of experiments in order to achieve the same guarantee. So that's a series of results telling us how a quantum agent could be much, much more powerful than classical agent. In the final part of my talk, I would like to dive into this experimental demonstration on the Sycamore processor. For the first set of experiments, we consider quantum advantage in learning about a physical state. Here, after learning an unknown state rho, we present the agent with two unqubit Pauli operators, Q1, Q2, and the agent has to predict which one of them has a larger magnitude in expectation value. And in figure B, we showcase the Sycamore processor. So in order to run this quantum learning algorithm, what we do is we consider this red one as an additional quantum memory of the quantum agent, where it can store an additional copy of the state rho and can perform an untangled measurement to obtain more information. And furthermore, in this experiment, we consider a hybrid quantum learning agent. So basically what we do is we have quantum agent doing the experiment. What it does is it stores two copies of the state in its quantum memory and then perform an entangled measurement to get some output data. We repeat that process for n times using a total of 2n copies of rho, and then feed that classical data into a gated recurrent neural network, where the gated recurrent neural network will then predict which of the two Pauli operators have a larger absolute value. And these are the results shown. So in figure B, we consider the training process of this hybrid quantum learning agent. We train this hybrid learning agent on noiseless simulation data, mostly in particularly this gated recurrent neural network part. noiseless simulation data for small system size n, where n equals to 2, 3, 4, 5, 6, and then predict on noisy experimental data obtained from the Sycamore processor. So the blue line shown here is the decay of training loss as the training progresses. Here we consider a cross-entropy loss. And this purple line shown here is the prediction accuracy of the hybrid quantum learning agent. So the higher, the better. It's basically 1.0 means perfect prediction, and 0.5 is equal to random guessing. We also showcase the prediction accuracy for the classical agent. So here we're using a best known classical agent, which corresponds to utilizing this classical shadow formalism in order to make the prediction. We can see that the prediction accuracy of the best known classical agent is only slightly above 0.5, where 0.5 is equal to random guessing. In figure C, we consider the sample complexity. We consider the number of experiments required to achieve a good prediction accuracy. Here we consider prediction accuracy of 70%. That is, for 70% of the time, the agent can accurately predict which one has the larger magnitude. The gray crosses shown here are the sample complexity for the classical agent. So in order to achieve 70% of the prediction error, the number of experiments required by classical agent, as you can see, scales exponentially. And so the cutoff here, like why do we cut it only at 8, is because for 10, the number of measurements is too high and we just couldn't get enough data before like the device is not working anymore. On the other hand, we also present this rigorous lower bound, which can be proven using similar proof technique to show that the least number of measurements, least number of experiments required by a classical agent to achieve this task. So as one could see, this scales exponentially as the system size. And finally, this purple line shows the sample complexity for using this trained hybrid quantum learning agent. And as you can see, at system size of only 20, we can already see a huge difference between the rigorous lower bound, which means the best classical algorithm that could possibly be conceived versus quantum agents. So in the next experiments, what we consider is the quantum advantage in learning about physical dynamics. So here is kind of a slightly different setting. We consider a collection of many different physical dynamics, half of which are general unitary dynamics, and half of the other which are dynamics that satisfy time reversal symmetry, which means that when written as a matrix, these evolutions, this unitary U corresponds to an orthogonal matrix. So starting from Dori Oharonov and Jordan Cotler and Xiaoliang Qi's work on quantum algorithmic measurements, they consider a site restricted class of classical agent and show that for those slightly restricted version of classical agent, it requires an exponential number of experiments to distinguish between the two. And then follow on top of that, in this recent paper published at Fox 2021, we also extended to show that for all possible classical agent, the number of required experiments also scales exponentially when one uses classical agent. And for this task, what we consider is we would train an unsupervised machine learning model to try to uncover this underlying symmetry structure. That is, the agents doesn't know what physical dynamics are general, what physical dynamics are T-reversal symmetric. It's just being presented with this collection of different physical dynamics, many of them, and then it has to figure out what are the underlying symmetry. In figure A, we showcase the setting. So for the quantum agent, what it could do is it could coherently access this physical dynamics. It would prepare some initial quantum memory, feed half of the quantum memory into the physical dynamics, get the output state coherently, do some quantum processing, feed the half of the quantum memory into the dynamics again, do some quantum processing, and make a prediction. On the other hand, the classical agent will prepare some initial state instructed by some classical bit string, evolve the initial state, and perform a measurement to obtain classical data. In both situations, we consider 1,000 access to these unknown physical dynamics. For each of the unknown dynamics, we have 1,000 access to it, and we consider a total of 100 different physical dynamics. And essentially, all the collected data for different K, E1, E2, E3 to E10, for example, here, we would path in through unsupervised machine learning model. Here we consider a Gaussian kernel PCA to learn a one-dimensional representation for all the dynamics. And the results are shown in figure B and C. In particular, here we consider both a 1D dynamics as well as the 2D dynamics implemented on the Sycamore processor. The 1D dynamics is shown like this light blue line, while the 2D dynamics is this 2D grid. This white thing is a qubit that's dead. And the results is shown in B and C. As one could clearly see, when one used quantum agent followed by an unsupervised classical machine learning algorithm, the classical agent, the machine learning model can accurately identify the two physical dynamics. On the other hand, when one uses classical agent, the results, the 1D representation is very mixed, and there's no clear separation on any pattern in this representation found by the ML model. Oops. So now to conclude, these theories of work have shown that classical agents are actually quite powerful in making prediction in the quantum world. As we said, it can accurately predict quantum phases of matter, it can accurately learn to predict ground state properties and so on. However, the boundary of their power still remains to be explored, especially when all the physical operations are not known perfectly. At the same time, our results have also shown that quantum agents can actually be extremely more powerful than classical agents. This is in stark contrast to most of the existing results on quantum sensing, which only provides a quadratic advantage. And due to this very significant advantage, in our demonstration on the Sycamore processor, we can show that the significant advantage in learning ability can still be evident using noisy intermediate scale quantum technology. And that's it for my talk. Thank you so much for listening.
Thanks a lot, Robert. That's really great. Let's see if there are any questions from the audience. Andrea, do you?
Yeah, there are a couple of questions that came up now. So maybe I'll read one of them. It says, are the resource budgets, so for example, the measurements, similar for the quantum and classical agents for the practical results on the Sycamore processor?
I guess he's probably asking about what is the, let's say, the depths of the measurements or things like that. So in both of these cases that we consider, due to the complexity of the dynamics alone, we're actually considering measurements that are only like constant depths. So in both quantum agent and the classical agent, so the classical agent is a constant depth measurement. The quantum agent is also a constant depth measurement. So in a sense, I think the answer is yes, they're similar. We're not comparing like quantum agent having a significantly deeper circuit, but the classical agent only has constant, where actually both of them only have a constant depth quantum circuit that's being applied.
So it seems like Hsin-Yuan has a question. Hsin-Yuan, can you unmute yourself? Maybe not. Okay, so possibly while we are trying to sort that out, we can start setting up the panel videos. So Robert, if you could stop sharing your slides. Sorry, was there another question?
Nice. There are interesting questions on in the question and answers.
Okay.
There's a question. Amazing work and lucidly presented. Well done. The examples of unlearnable settings seem to indicate that even a little bit of irreproducibility in experiments renders learning impossible. What does this say about the scientific method in the real world?
Oh, that's a very big question. I'm not sure. Yeah, so for the examples that I gave, there are literally settings where it's just impossible to distinguish. So I guess when you really do science in those kind of regime, you're just not going to figure out that underlying process. Like, for example, maybe one of them has dark matter while the other doesn't have it, but there's no ways to distinguish them. So that could happen. I don't think the current scientific methods that people are using are actually wrong in any sense. It's just there are situations where they are just impossible to learn. So I don't think it undermines the scientific method or it's, yeah, but that's a very, very interesting question.
I think Hsin-Yuan is now.
Robert, can I maybe add something to your response?
Yeah.
Which is that if you follow the proof through, then what comes out is the reason it's unlearnable is the existence of a certain noise floor. And so you can quantify that. That it prevents you from learning to arbitrary precision. So I think there's a sort of chicken and egg game that you can play where you can exchange epsilons and deltas a little bit and say, well, if I want more precision, then I just need to increase, I need to, change delta to be delta over 2, and now I can move epsilon down a little further and vice versa. So I think that it doesn't undermine the credibility of the scientific enterprise. It just means that in order to get more precise and reliable answers, you're going to have to sharpen the questions that you ask and the apparatus which does the probing. And as long as you continue to ask sequences of questions that can converge to the other theorem that Robert presented, which allows you in some limit to look at unitary dynamics and pure states, then things should be learnable.
Okay, so may I ask you a question? Sorry for for the technical problems. Well, thank you very much for the inspiring talk, Robert. My question is, most of the examples you talked about is dealing with either quantum state or quantum process. So it's in some sense intrinsic quantum problem because the input is quantum, but the answer is like classical. Do you think there could be some separations for the intrinsic classical problem, say optimization problem, or completely classical settings, but using quantum algorithm?
Yeah, that's a great question. I think a lot of the panelists here have thought deeply about this question. I think at the moment it seems like it's still very unclear. Like there are results by many people showing that the advantage is at most this and some of that. So I think it's possible to have advantage, but exponential ones, I'm not that sure.
Well, there are the results of about the welded trees and the recursive Simon's problem that basically do show an exponential separation. Wouldn't you say, Robert?
Yeah, but in a sense, those are also quantum oracles, right? So you access them as kind of like a quantum way. So in a sense, it's still kind of quantum. It's because of the oracle nature. Like we're comparing a classical oracle versus when you have a quantum access to it. But so those are, yeah. But so I'm not entirely sure if that would actually happen in practical setting. And even in those cases, like those examples, you still have to have coherent access to these processes in order to get the advantage.
Yeah, right. But yeah, you're comparing a classical oracle to a classical oracle when the access to it is coherent access.
Right. But I guess Hsin-Yuan is more thinking about the setting where the access is all classical, like it's complete classical access, and whether we can still have advantage in those kind of setting. Because I guess if we want to access some problem with quantum access, then in effect that oracle or that process itself must still be some quantum mechanical process so that you can access it quantum mechanically, right? If it's completely polarizing, then like if it decoheres everything, then we're not going to gain this coherent access to like the Simon oracle or this like well-to-tree oracles and so on.
And speaking of that, relate to this, at some point you mentioned that this separation happens only for the without entanglement.
Yes.
But that does not imply that you can apply for the classical settings. Like what makes it quantum in that context?
So in that context, they're still quantum systems in the sense that they're quantum particles. They're like atoms. They're not entangled. There are some classical correlation between them, but they're completely unentangled. So it sounded a bit like classical, but it's still not quite, in the sense that they're still quantum particles. And it's because of the underlying sort of uncertainty principle at play. And that's why you have quantum advantage. It's because there are uncertainty principle when you interact with it classically, like when you do measurement on top of it. But when you can store multiple copies of them in a quantum memory and do like quantum data processing, you can avoid these kind of uncertainty principle. And that's sort of the root of the cause of disadvantage. So I wouldn't say they're intrinsic classical. I think intrinsic classical must be like the data is completely just bit strings, and looking at that data using classical agent versus quantum agent can yield a separation. For those kind of tasks, I think the most well-known is Shor's algorithm, but other than that, it still seems a little bit like we have polynomial speedup, but for exponential ones, it's less clear at the moment.
Thank you.
Okay, great. Well, thanks. So shall we, if we can get the videos of all the panelists pinned up. And let me start by